convex risk-bounded continuous time trajectory planning in uncertain non-convex environments. In order for robots to navigate safely in the real world, they need to plan safe trajectories to avoid static and moving obstacles such as humans and vehicles under perception uncertainties. In this work, we address the trajectory planning problem in such uncertain, static and dynamic environments. In this problem, the time-varying, probabilistic, and non-convex nature of the obstacle-free safe regions makes the trajectory planning problem challenging. To address a trajectory planning problem in uncertain environments, we provide a risk-bounded trajectory planning method that looks for continuous time trajectories with guaranteed bounded risk. In this problem, risk is defined as the probability of collision with uncertain obstacles. We reformulate the risk-bounded continuous time trajectory planning problem as the following probabilistic optimization, where we look for continuous time trajectory xt defined over the planning time horizon between the start and final points, such that the probability of collision of the trajectory with uncertain obstacles is bounded by the given acceptable risk level delta. In this problem, we represent uncertain obstacles in terms of polynomial level sets with uncertain parameters. Such polynomial level sets allow us to represent obstacles with probabilistic location, size, geometry, and trajectory with arbitrary probabilistic distributions. Solving the probabilistic optimization of the planning problem is challenging. This is because we need to deal with multivariate integrals of the probabilistic constraints defined over the non-convex sets of the obstacles. We need to deal with time-varying constraints to ensure that they are all satisfied over the entire planning time horizon. And the defined optimization is in general non-convex. Hence, we cannot guarantee to obtain the global optimal solution. Existing approaches to address risk-bounded trajectory planning problems provide approximate solutions by using either simplified models or sampling-based methods. In this work, to solve the probabilistic optimization of the planning problem, we first leverage the notion of risk contours to transform the probabilistic optimization into a deterministic optimization problem. Next, we provide convex methods based on sum of squares polynomials to efficiently solve the obtained non-convex time-varying deterministic optimization problem. Unlike the existing planners, the provided planning algorithms obtain the continuous time trajectories with guaranteed bounded risk without the need for time discretization. They also deal with arbitrary probabilistic uncertainties, non-convex, static and dynamic obstacles. Risk contours are the set of all points in the uncertain environment with guaranteed bounded risk. Risk contours of all uncertain obstacles represent the feasible set of the probabilistic optimization. In this work, we provide an analytical method to compute an inner approximation of the risk contours. Provided analytical method relies on higher-order statistics of probabilistic uncertainties and upper bound indicator function of the obstacles. Using the provided analytical method, we obtain a polynomial-based inner approximation of the risk contours in terms of the polynomial of the obstacles and moments of the uncertainties as follows. Any trajectory inside the computed risk contours is guaranteed to have a risk less or equal to delta. Here is an example of computed risk contours. In this example, probability of collision with the uncertain obstacles inside the obtained risk contours is close to zero. Provided inner approximation of the risk contours allow us to transform the probabilistic planning problem into a deterministic planning problem as follows, where probabilistic constraints are replaced with deterministic constraints in terms of the computed risk contours. In the next step, to solve the obtained deterministic time-varying non-convex optimization, we provide sum of squares-based techniques, including sum of squares-based convex optimization that transforms the deterministic optimization into a convex optimization of the form of a time-varying semi-definite program, and sum of squares-based RRT algorithm that uses sum of squares-based convex constraints to ensure safety along the edges of the RRT with respect to the risk contours without time discretization. This is an example of risk-bounded planning in the presence of dynamic obstacles with uncertain size and trajectory. At each time t, probability of collision with uncertain obstacles inside the obtained risk contours is close to zero. We can also use the provided method to compute the risk contours in the presence of highly complex, uncertain, unsafe regions. Please check out the paper for more details and results on planning problems of autonomous and robotic systems.